Hi folks, welcome to this video on differentiability, where we sort of nitpick where we can actually find slope on a function. So differentiability means slope findability. Where can you actually talk about the slope? And for most functions, you can talk about it everywhere, but the kind of points that we need to watch out for are things like this, and we alluded to this in the last video. If you have a corner on a function, something like this, so there's the function y equals absolute value of x. Okay. Right here at this sharp corner, you can't find the slope. So this function is differentiable everywhere except at x equals 0. Similarly, if you have a cusp, so a cusp is something that looks like how a mediocre artist like me draws a seagull. Looks kind of like this from one side. It's the sharp meeting point of curves, okay? Whereas a corner is the sharp meeting point of lines. So at x to the 2/3, neither of these are differentiable at x equals a. Or at x equals 0, rather. Okay. Everywhere else, they're fine. You can talk about their slopes. Together, these two make a class of points that we could just call sharp points. Sometimes we get really nervous about, like, if we had something that looks like a cusp from one side and a corner from the other, what should we call it? It doesn't matter. It's a sharp point. You can't talk about slope there because the slope is not gently coming to the same value from each side. It is different from us having something like this. That kind of vertex happens with a slope easing off and going towards 0 from either side. It's nice and smooth. And those are the kind of turning points that we see more commonly. The other kind of slope that is an issue is something like this. If you had something that went just momentarily vertical. Okay. So just at x equals 0, it's going to a vertical slope. That will happen on something like a cube root graph. This is a different type of problem than we have in number 1 and 2. The reason we can't talk about slope here is because vertical slope is undefined. Right? It would have infinite rise over no run. And division by 0 continues to be a problem. So this function that I just drew here is also not differentiable at x equals 0. It is okay everywhere else, though. Lastly, we at all our discontinuities, we're going to have problem finding slope. So let's imagine that we had a function that did, I don't know, maybe it does this. It has a vertical asymptote at x equals -1. And it does something wacky around here. It's going to come down like that. And have a jump in it. And there we go. And it's got a removable discontinuity at x equals 1. And then, let's just have it go off to the side nice and smoothly. There we go. Something like that. This one is not differentiable at x equals -1. Okay, that's a discontinuity, an infinite discontinuity. It's also a domain issue, so I mean it's ridiculous to look for the slope where the function doesn't even exist. It's not differentiable at 0 because they're not connected there. Any discontinuity means that we can't talk about the slope at that point because it's just weird there. And at 1, there's a removable discontinuity. And so that tells us that differentiability is like a more strict thing to look for than continuity. Okay? Differentiable functions, or functions that are differentiable at a given point, is a subset, continuity, of continuous functions. So if a function is differentiable at x equals a, then it is automatically continuous at x equals a, because discontinuity means not differentiable. So let's take a look at that in the context of a weird looking graph. This is a function that exists mostly over the domain -3 to 4, -3 to +4. And it has one spot where it doesn't exist there, but we're not going to get too carried away with that. We're asking, where is it not continuous? So the simplest definition of continuity is, where do I have to lift my pen? Oh, I have to lift it at x equals -2. If it's not continuous there, then it is not differentiable there either. I cannot talk about the slope at -2. Where else is it not continuous? Well, it's not continuous at x equals -1. I have to lift my pen there as well. So again, if it's not continuous at x equals -1, it's not differentiable there. Let's see if there are any other issues in this function. So I'm just going to trace it through. Here I can find slope, no big deal. Slope is 0. Slope is 0. Over here at x equals 2, oh, there's a problem. That's a sharp point of some kind. So the slope is different from each side. Over here at x equals 3, there's another sharp point. Those are places we couldn't talk about slope. There's actually one other place on this function, though. I'm going to trace it through one more time. So can't find slope at -2. Can't find slope at -1. Discontinuity there. This is okay. Slope of 0 is fine. But right here, it goes momentarily vertical. Right? The slope or the tangent would be vertical. So at x equals 1, I'm going to do this in red, lest anyone think that the green means it's okay, as a vertical tangent. So slope would be undefined there. The function still exists there. There's still sort of a limit going towards a slope of infinity or -infinity, but there's no number for vertical tangent. So to recap, 2 places where it's not continuous, they guaranteed it wasn't differentiable at those points, but there were 3 other places where we also had not differentiable, for a grand total of 2 places where it's not continuous and 5 places where it's not differentiable. Finding issues in differentiability tends to boil down to either generating the graph and looking for them, or finding the derivative function and seeing what numbers cause issues in that. For now, we're going to look at the graph, but we'll revisit this very soon in the context of algebra. So where is this not differentiable? Well, I know that an absolute value function is just a v. This one has been moved left 3 and down 2. So if I were to just make a quick and dirty sketch, something like this. And I can see it's not differentiable at -3. There's a sharp point. That's also sort of the most fishy value in the whole function, right? That's where the absolute value signs might start kicking in and doing something to either the left or right of 0. So if you looked at these next ones, we are going to look at Desmos to get an idea of these weird functions. But you can already tell what are the fishiest values on them. So let's look at sine of absolute value of x. I go functions, I choose sine, I use my absolute value symbol. Okay. And there it is. And you can see right at 0, there's a sharp point. Let's get the other one while we're at it. So under functions, I have to go down a fair bit here. And there's my nth root. Okay, so cube root of 2x minus 8 was the other function. And it looks pretty continuous everywhere. The only thing is, at x equals 4, it looks like it might be vertical. Let's really zoom in. Oh, yeah. Oh, geez. That really does go vertical, just momentarily. Okay? So those are the types of problems we run into here. Let's write them down. There's a differentiability problem at x equals 0. It was a sharp point on this one. It looked very much like a cusp. You can say cusp. You can say sharp point. Doesn't matter. And on this one, it was x equals 4, and it had a vertical tangent at that point. Now, sometimes the book will ask you, where is it differentiable? It's okay to say everywhere except x equals 0. So if the question is set up sort of the opposite way around, we say everywhere except where there's a problem. Speaking of which, here's some practice questions from the Finney 4th edition calculus textbook, AP Calculus textbook. There are some even answers. And in the end, we're really just hunting down trouble spots in slope, namely sharp points, vertical tangents, and discontinuities. I hope this has been helpful. Good luck with the material, folks, and take care.